All right, right now I'm coming to you from Cornell's hydroelectric power plant, and we've had a lot of rain recently, so as you can see, Fall Creek is flowing pretty heavy from BB Lake. Now, this right here is that hydroelectric power plant. We use water, or flowing water, as a great analog for direct current electricity, but how is it we get electricity, several 100,000 kilowatt hours of electricity from this particular power plant? It has a lot to do with all that flowing water you see coming out of it. But the thing is, they actually decrease the amount of water flowing through in times like this when there's a whole lot of flow. So like, why do they do that? Is that a waste? Could they be generating more power, more electricity if they didn't throttle it down? That's one of the questions we're going to have to answer. But hydroelectric power, or hydroelectric generation, is one of the ways we generate current electricity.
More from the power plant later. Right now, I'm just going to quickly shoot through a little bit of notes. You can pause it at any point. I'm not going to talk a whole lot here because I really don't need to. You already did a pretty good job going through those two simulations that allowed you to explore resistivity in a wire and Ohm's law, but just shooting the relationships at you real quick. Here we go. Alright, so resistance is measured in ohms, as I said before, and we actually use Ohm's law to figure out the current, resistance, and voltage situation or relationships inside circuits. So that's our thing that we finished off with last time. Ohm's law looks like this. If you want to find the current in a circuit, you simply take the voltage of that circuit and divide it by the total resistance. So total current is total voltage divided by total resistance. Current can be different in different parts, but we're not worrying about that just yet. As we start breaking apart our circuits into more useful things. Right now, there's our first form of Ohm's law. Second form of Ohm's law, you want to find resistance. Hey, do some algebra. You just mix things around. Resistance of a circuit, or part of a circuit, is equal to the voltage across that part divided by the current running through that thing. So if you have a resistor like a light bulb, the resistance it offers in ohms is equal to the voltage that's applied across the resistor divided by the current running through that resistor. Okay, and we'll use the example of light bulbs in a few seconds. Straightforward right here. If you have a 9-volt battery supplying power to like a cordless curling iron or some other appliance, you know, just figure this was a small one, and it has a resistance of 18 ohms, that means the resistance offered by the curling iron is 18 ohms. The 9-volt battery is your voltage supply. How much current is flowing through the curling iron? So if I want to find voltage, I'd use this equation. But I'm not trying to find voltage, I want to find current. So we simply go back, boom, boom, right there. Current is voltage divided by resistance. So if current is voltage divided by resistance, you could also just do the algebra. I would take 9 volts divided by 18 ohms, and I get half an amp of current. So boom, real fast right there. If I put something in right here to measure current, it would say, come on now. So if I put what's called an ammeter right here that measures current, A right here, it would say we have 0.5 amps of current. That's I. Okay? Simply using Ohm's law becomes more useful when we have a more complex circuit. Alright, now onto this idea of circuits. The other thing I had to explore was a simple relationship with what a resistor is made of and how much resistance it offers. So resistors and how much resistance they offer depends entirely on how long they are, how big around they are, and what they're made of. Okay, so resistivity, this thing right here, that has to do with the actual atoms that make up the metal wire and how many electrons they have. Alright, so you get a set value for resistivity. Length, in general, the longer your wire, the more resistance it's going to offer, because if you have a voltage source like 5 miles away, it's got to push 5 miles. That's a whole lot of copper it's got to push through. So, longer wire, greater resistance. But if you have a larger, thicker across wire, that's going to decrease resistance because you have a lot of surface area that it travels across. And current does travel across surface area, so the larger your wire gets, the easier it is to send current through it. But when you have really, really big wires like power lines that run hundreds of miles, they're not solid pieces of copper like this, even though, you know, the bigger this area is, the less resistance it offers. At some point, you get this weird thing called the skinning effect, and essentially, all the charges travel on the outside of the copper wire. Why on the outside? Well, because they're all like charges and they push away from each other. The bigger the wire, the larger the outside surface area. But then you have all this wasted copper in here. So what we do is we actually have braided copper wire, a big thick wire made of smaller wires that actually increase the amount of surface area offered. So even though they're made out of smaller wires, they take up almost the same amount of space as this. They will allow way more current because they have more outside surface area. And there's basically less waste. That's just a little bit of electrical engineering right there. Okay, so resistivity is what a material is made of. L is the length of that resistor or that wire. And then A is the cross-section area. So if you're given a problem like this, determine the resistance of an 8 meter, boom, 8 meter length, of silver wire. Silver, that will be tied to the resistivity, and it has a diameter of 0.4 meters. Well, you've got a circular wire, so you'd have to use the area of a circle, pi r squared. We're cutting this in half, we get r, plug the numbers in, boom, you get a resistance value. The resistivity is usually given on tables like this. You can see right now, let's see, I think what I had on that previous page, what was that, copper? No, silver wire. Alright, so, silver wire, there's its resistivity. The resistivity units is ohms per meter, or ohm meters, sorry. And as you can see, silver's a decent conductor. Gold, the smaller this number, the better the conductor is. So, you know, let's see, there are quite a few of these that are actually not that great, but like glass is a terrible conductor, lucite quartz, all these things are terrible conductors. They don't let electrons move, that's why we call them insulators. So everything else has a fairly low resistivity in comparison because it lets electrons flow. And that's basically a recap of the work you already did. Okay, that Ohm's law simulation, the resistivity simulation. Change the material, change how much it resists, change the length, longer it is, more resistance, shorter it is, less resistance, bigger the wire, less resistance, all those relationships right there in those equations. But now I want to get on to the actual thing, the circuits, which goes back to the idea of that power plant. So here we go. Please write down that a simple circuit, and the way I'm going to compare this is I'll compare it to the BB Lake hydroelectric power source. The simplest electrical circuit consists of a source of electrical energy. That's going to be our voltage, our power supply right here. Alright, a battery, like this is in this case, connecting wires. So these wires, we'll pretend they're copper. We're not going to calculate anything of them, but copper is a really good conductor. And circuit elements such as a lamp or a resistor that converts electrical energy into heat or light. So these are technically resistors. Alright, so current's going to flow. It's going to go through here. It'll convert some of that electrical energy into light and heat, and then it continues on, and then whatever voltage was not used up by this guy gets used up by this one, powering this light, and then it goes through, again, if you have your switch open or closed, you know, closed switch, it's like turning on a light switch. Electrical energy flows. Open switch, nothing flows. So you need to have a complete circuit. Alright, and here are our symbols, what I'll use to break down the dam at least a little bit. We have power sources, can be labeled like this. A cell, like a power cell or a solar cell, those are going to be labeled like this. Typical battery will be like this, and if it's something like a big power supply, which I would be using in the classroom with you, it would also be kind of like the battery. Switches look like an open door in an old blueprint. This is an open switch, closed, boom, it'd just be shut. If we're measuring voltage, we use a voltmeter. There's the schematic for that. There's schematic for the ammeter and our typical resistor. Of course, we usually have like little legs coming off the resistors like this. But there's our resistor. We won't be using variable resistors in our circuits, but you use them all the time. If you have anything that's got a volume button or a volume knob, what you're doing is changing the resistance to current flow to your speakers. You decrease your resistance, guess what? Current flow increases, speakers get louder. You You increase the resistance, the speakers get less current, things get quieter. But we're not really going to be using this one in any circuit. And instead of writing a lamp like that, we typically will just consider our lamps resistors. So these are the ones we'll focus on. Special ones, capacitors, we already know look like this. And then an LED, which we will have in different circuits. They look like this, a triangle going into a straight line. These arrows basically represent energy leaving the LED in the form of light. But you can also have something that looks like an LED schematic with arrows going in. We call that a photosensor. And if you have a garage door opener with a safety mechanism where if the garage door is shutting and you're walking underneath it, and it stops and doesn't hit you in the head, that basically means you have one of these that doesn't give off light, but it takes light in, and there's an invisible beam going across your garage. The only other thing that you might find with an LED symbol is a little circle going around it. So those are the two ways we might see them. In our next bit of notes, I'm going to take you through the dam, the dam to the hydroelectric station, and just break it down like it's a circuit, and talk to you about different things like potential drop, and then we're going to move right into series and parallel circuits and getting back into that logical puzzle solving nature of electricity. Okay, thank you for paying attention.